Why does a wagon need wheels? The answer to that question is that a wheelless wagon would struggle against friction whenever it moved or tried to move. The motion of an ordinary wagon, that is, one with wheels, resembles that of a skater. When you leave them alone, they're inertial and they move according to Newton's first law of motion. If they're at rest, they remain at rest. If they're in motion, they continue in motion at constant velocity. Remove its wheels, however, and the wagon exhibits entirely different behavior. If you push it, it moves. If you stop pushing it, it stops. That behavior is not the least bit surprising, but it should be disturbing. Not disturbing in the sense of call the police or a psychiatrist, but disturbing in the sense that it goes against many of the physics concepts that I've been talking about up until now. Why doesn't the wheelless wagon coast when you leave it alone? The issue is this. According to Newton's second law of motion, for the wheelless wagon to accelerate to a stop, to decelerate, it needs a net force acting on it in the direction opposite its velocity. What could possibly be exerting that force? The answer is friction. In addition to its downward weight, a gravitational force, and the upward support force from the sidewalk, the wheelless wagon can experience horizontal frictional forces from the sidewalk. And it's those frictional forces that slow the moving wheelless wagon to a stop when you leave it alone. The pervasive influence of these frictional forces in our world explains why early scientists and natural philosophers didn't understand inertia, and why it took the genius of Galileo and Newton to recognize inertia for what it is. The moving wheelless wagon doesn't slow to a stop because it lacks inertia. It slows to a stop because it's experiencing a non-zero net force, and it therefore accelerates in accordance with Newton's second law rather than coasting according to Newton's first law. For a wagon to move according to Newton's first law, it has to be free of net force, and thus free of the slowing effects of friction. That's why a wagon needs wheels. Frictional forces are exerted by surfaces on one another. And like all forces, they appear in Newton's third law pairs. When the sidewalk exerts a frictional force on the wagon must exert a frictional force back on the sidewalk that's equal in amount and in the opposite direction. Frictional forces act along surfaces, parallel to surfaces, which distinguishes them from support forces. The support force that this sidewalk is exerting on the wagon is straight up, perpendicular to the horizontal sidewalk surface. Any frictional forces that the sidewalk exerts on the wagon, however, are parallel to the surface. In this case, horizontal. So as I scoot our poor wheelless wagon, I feel sorry for this thing without its wheels. As I scoot it around on the sidewalk, frictional forces are pushing the wagon horizontally. At the same time, the wagon's frictional forces are pushing the sidewalk horizontally. You don't see the sidewalk. Okay, it's a table, but I'm calling it a sidewalk. You don't see the sidewalk moving not because it fails to have forces on it, but because it's attached to the whole world, including the camera through which you're viewing us, and so you cannot see the sidewalk's response. But it's there, it's just very small. So as I scoot the wagon about, horizontal frictional forces from the sidewalk are affecting its motion. The frictional forces between two surfaces oppose any relative motion of those two surfaces. In other words, the frictional forces act to bring those two surfaces to the same velocity, so they move together rather than sliding across one another. To illustrate this idea of relative velocity, let me have two surfaces that I can talk about easily. This book surface and my hand. Right now, the two surfaces are not in relative motion because they have the same velocity. They're both motionless. But they'll still have the same velocity if I move them steadily along to your left or if I move them steadily along to your right. There's still no relative motion. Relative motion then is not about whether the book is moving or whether my hand is moving. It's how one is moving relative to the other. Or if you think in terms of perspective, from the perspective of the book, technically known as the frame of reference of the book, my hand appears motionless. It still appears motionless. It still appears motionless. So if you could imagine yourself a tiny person or maybe a bug sitting on that book surface, my hand looks motionless to you no matter what I'm doing here. But if I begin to move my hand relative to the book, like this, from the perspective of you sitting on the book, the little person, you go, well, that hand is moving. So this now is relative motion. But so is this. It doesn't matter whether the book is moving or my hand is moving. It's one as viewed from the other's frame of reference. So, relative motion. Friction opposes relative motion. And it even opposes the start of relative motion. With that then, let's return to the wagon on the sidewalk. Now, the sidewalk is attached to the whole earth, so you're not going to see it respond to forces. It's just going to stay put. So its velocity is zero, and pretty much no matter what we do to it, its velocity is going to stay zero. Right now, the wagon is motionless, the sidewalk is motionless, and so the two of them are not in relative motion. But let me start some relative motion and watch what happens. Ready? Get set? I started it. And lo and behold, the wagon, which was sliding toward the right, came to a stop. A frictional force from the sidewalk acted on the wagon to slow the wagon to a stop. That frictional force in this case was to your left. Right? Let's say it again. It's a leftward frictional force. It caused a leftward acceleration of the wagon, bringing the wagon to rest. Let's reverse the motion. I'm going to now skid the wagon to your left. Whoa! Friction's smart. The frictional force of the table on the wagon now pointed toward the right and caused a rightward acceleration of the wagon, bringing it to a stop. So, no matter what I do with the wagon, the frictional force from the sidewalk pushes on the wagon in the direction that slows the wagon's velocity and brings the wagon's velocity to the same velocity as the table, namely zero. So, frictional forces overall, they act parallel to surfaces, that is, along the surfaces, and they act in the direction that opposes relative motion of the two surfaces. If the two surfaces are stopped, they are not in relative motion. That doesn't mean that frictional forces are absent. It means that those frictional forces, if they're present, are opposing even the start of relative motion. For example, if I give a little bit of a push to the wagon, I'm trying to get it started. And in the absence of friction, I would be causing the wagon to undergo acceleration. But nothing happened. So a frictional force developed, frictional force pair actually, developed between the wagon and the sidewalk, causing the wagon to remain motionless. That brings me to a question. When I hold a beverage can between two fingers, one on your right and one on your left, am I exerting any frictional forces on the can? And if so, in which direction do those frictional forces on the can act? I'm exerting upward frictional forces on the can, and those frictional forces are what are supporting the can's weight. Without those frictional forces, the can would literally slip through my fingers and fall to the ground. Since wagons move on stationary sidewalks, a wheelless wagon is going to have serious problems with friction. You'll have to push it hard to overcome the opposition of friction in getting the wagon started. And once it is started, you'll still have to push it every step of the way.